Very good evening to all of you. It's my proud privilege to introduce today's special lecture speaker, Professor Bimla Buti. This is the special lecture series of Vigyan Vidushi program, which is a 3-week program, and we are having quite a few special lectures in this. We are very, very fortunate to have Bimlaji today with us. She is a physicist of eminence, mainly working in the plasma physics and related areas. She got PhD from University of Chicago under Nobel laureate S. Chandrasekhar. Then she was a faculty at Physical Research Laboratory till her superannuation. She has lot of firsts to her name. I will be able to give you only a short glimpse of her very, very inspiring career. When you will hear her, you will really see how inspirational she is, and is a great role model for many of us to uh, get motivated and also learn from her work. So she was the director of the plasma physics at ICTP, International Center for Theoretical Physics, during 1985 to 2003. She's also been associated with various NASA centers, Goddard Space Flight Center, MS Research Center, and Jet Propulsion Laboratory. She's published a large number of papers and edited 4 books. During 1977 to 83, she was an associate editor of IEEE Transactions on Plasma Science. She founded the Plasma Science Society of India and worked as its president during 1992 to 93. She served as the president, Commission 49 of the International Astronomical Union. Professor Buti was the first woman physicist to be honored as an INSA fellow and the first Indian woman scientist to be elected as a fellow of the World Academy of Sciences. She is fellow of National Academy of Science, fellow of American Physical Society, and is also a nominated member of American Association of Advancement of Science and Sigma Xi Society of US. She is recently featured in the APS bulletin, which has come out on the history of science in India. The Professor Buti received Vikram Sarabhai Award for Planetary Sciences, INSA Jawaharlal Nehru Birth Centenary Lectureship Award, INSA Venubapu Medal for Astronomy and Astrophysics, Professional Achievement Citation Award of University of Chicago, American Geophysical Union Medal of Fundamental Contributions in the Physics of Nonlinear Waves and Chaos, Professor Meghnad Saha Memorial Award of National Academy of Science India, and Nasi Professor A.C. Banerjee Award. She has also made significant contributions to the gender question in science. To encourage women to go for a career in science, she has instituted a number of awards exclusively for women scientists through her foundation, which is Buti Foundation, and we will share the address of the site with you. It's very appropriate to have her give this talk today on chaos and fractals in science as a part of this Vigyan Vidushi serial. And I'm sure you all will enjoy this talk and count yourself fortunate. Indeed, all of us are very fortunate to have this opportunity of listening to her. Over to Professor Bimla Buti. Bimlaji, you may start.
Thank you very much, Vanna, for your kind words. And I would also like to extend my personal welcome to all the young students who are here as participants. And as Vanna has already announced, that I'm going to talk about the subject of chaos and fractals, and also would like to give you the applications of chaos and fractals, not only in science, but in technology also. You might wonder as to why I have decided to talk on this somewhat complex topic. There are 2 reasons for that. The first one is that the organizers had asked me to talk about my own work for obvious reason. And second one is, through this lecture, I would like to convey a message to the young students in the audience that there is nothing complex. Once you are passionate about something, then you can, after doing hard work, you can achieve whatever you would like to achieve. And hopefully, I would convey this message through this talk, which will be about 40-45 minutes. I realized that most of you are not familiar with the subject, but don't worry about that part. I will be defining each and every term that I use in this lecture. So let's get on to the lecture. The subject of chaos is truly interdisciplinary. It occurs in a variety of physical systems, for example, astrophysics, condensed matter physics, optics, plasmas, fluids, and so on. And it also occurs in biological systems, chemical systems, atmospheric science, ecology, neural networks, biophysics, and so on. Some scientists feel that study of chaos is an abstract one, but I can tell you it's not so, and I'll show you that it leads to a large number of very useful practical applications. The mathematical techniques which are used to study chaotic phenomena in any of these systems which I have listed in my previous slide are the techniques of nonlinear dynamics like Poincare maps. Okay, and I have shown the simple Poincare map here, which transforms the point P to a trajectory TP, which is defined by the first re-entry point of the trajectory starting at point P. Now we will be using these Poincare maps during our discussion left and right. You may be surprised that our human heart is a nonlinear dynamical system. Historically, it was Jules Henry Poincare who was the first person to recognize the chaotic behavior of a dynamical system. He encountered this unexpected behavior in his studies of three-body problem in planetary systems. And to remind you of our beautiful planets in the solar system, here is the picture that I am showing you. I have highlighted the word three-body. Emphasize the fact that the minimum number of degrees of freedom of a dynamical system to be chaotic is 3. And I will come back to this during the discussion of this lecture. I'm going to develop this subject by posing some pertinent questions to myself. For example, how exactly do we define a chaotic system? What should we look for to distinguish it from a normal system? Can chaos be simply equated to disorder in system? Is there any correlation between chaos vis-a-vis fractals? And I'll try to answer these questions one by one. First, the definition. There is no unique definition of chaos. The simplest way it can be defined is as follows. If we map the trajectory of a particle in a given field, and if the trajectory is not smooth but scattered, then the system can be chaotic. And I emphasize on the word can be. It may be, it may not. The scattered mapping, in fact, is a necessary condition, but we need to satisfy the sufficient conditions also. Another necessary condition for a chaotic system is its extreme sensitivity to the initial condition. In other words, if we take the two neighboring trajectories with slightly different initial conditions, these trajectories must diverge exponentially. Here I have given you the two qualitative definitions, but we are physicists. We should not be satisfied simply with the qualitative definition. We've got to worry about the quantitative ones. Quantitatively, the sufficient condition for the chaos to take place is defined what is known as the Lyapunov exponent L, which is defined by this very simple relation. D is the physical distance between two neighboring trajectories. If we find that the Lyapunov exponent L is a positive quantity, that is L is greater than 0, then we are dead certain that the system is going to be chaotic. L greater than 0 is both sufficient as well as the necessary condition. So that is the reason when this condition is satisfied, we can be dead certain that we are going to see chaos in the system. Lyapunov exponent plays an extremely important role, and as I showed examples.
Bimla ji, your mic has become mute. 1 minute.
Is it okay?
Yeah, thank you.
I didn't mute it. I think it was done from your...
Yeah. It happened. It's not your mistake. Sorry. Right.
Okay, next. Is chaos simply a disorder in the system? And the answer is no. Chaos cannot be simply equated to disorder. At the most, one can say chaos is a periodic disorder. I'll show you later that chaotic regime is not just one continuous regime of irregularity. It can contain windows of order within disorder. And I'm going to illustrate the things that I have talked about so far through some examples. And the simplest example that I can think of, especially for the physicist, is that of a pendulum or a harmonic oscillator. Supposing the oscillator is moving in simple potential given here, then the top figure is simply showing you the energy diagram, whereas the corresponding figure below gives you the phase space orbits. You see the closed trapped orbits, and you also see the untrapped orbit. And the orbit separating the two, which is called the separatrix, is labeled by energy E3, which corresponds to the maximum of the potential. Now, here we see very well behaved orbits. So obviously, since there is no scattering whatsoever, this system can never be chaotic. However, if we apply some force from outside, so in the presence of an external driver, even this simple harmonic oscillator that we are familiar with, let's see what happens to that. At certain strength or the amplitude of the driver that we have introduced now, we find that the period of oscillation becomes double. This is what is called period doubling bifurcation. At some other strength of the driver, there's another period doubling bifurcation. Here also, so period becomes 4. And this keeps repeating itself, and eventually what you find is that the system, which was completely periodic system in the absence of a driver, becomes a chaotic system. And I will use this analogy when I discuss some other examples. But before I go to the discussion of chaotic phenomena in plasmas, I would like to define another very interesting term called strange attractor. We know that in non-dissipative system, phase space is conserved. But in a dissipative system, phase space can shrink. The patterns that a dynamical system tends to settle into are called attractors. In simple non-chaotic system, the attractor can be a point in 0 dimension, a line in 1 dimension, similarly a plane in 2 dimensions, and so on. But in chaotic system, the attractor can have a complex structure, and besides the complex structure, it should have fractal dimension. We have never heard of fractal dimension in our regular non-chaotic system. And such an attractor, which has a complex structure and also has fractal dimension, is known as the strange attractor. And also sometimes it's called the chaotic attractor. Historically, the first strange attractor was found in 1962 by Lorentz and is known as Lorentz attractor. It's not known as strange attractor. The reason for that is the name strange attractor was coined much later in 1975 by two mathematicians, Reuel and Tucker. And here I'm showing you the Lorentz attractor, which is strange attractor. It has a complex structure, but in spite of that, it looks so beautiful here. Here is the Lorentz who discovered this. Now let me go and talk a little bit about my own work. Here I'm going to talk about chaos in magnetoplasma. You know, in most of our space and astrophysical plasmas, they have embedded magnetic field. And in such plasmas, we can have a variety of large amplitude waves. However, for sake of illustration, in this lecture, I will confine myself to nonlinear Alfvén waves because these waves have been observed by a number of spacecrafts. And just to give you a feeling of what Alfvén waves are, these are nothing but transverse waves and which define the oscillation, the fundamental electromagnetic oscillation prevalent in magnetic confined plasmas. I would also like to stress upon the fact that a nonlinear wave in general is equivalent to a nonlinear dynamical system, which exhibits phenomena of chaos under some specific conditions. So let's see when and under what conditions this can happen. So in order to find out and study these waves in details, we ought to find out what is an evolution equation that governs these nonlinear Alfvén waves. We have to derive this equation starting from the fundamental magnetohydrodynamic equation. We have derived it, and the evolution equation is shown here. You immediately see that we have a vector equation with two magnetic field components, By and Bz, since we have taken the propagation along the x direction. Take my words that this equation governs the elliptically polarized Alfvén waves. We, the physicists and the mathematicians, know very well that even to solve a single nonlinear equation is not a child's play. So what do we do with this? We have coupled nonlinear equations. Should we give up? Answer is no. And this is where I would like to give you my friendly suggestions that when you go for your research career, very often you will come across such difficulty. But don't give up. Simply don't give up. Okay? What we scientists try to do, we try to find the maximum information out of the equation that we have derived. For example, supposing I say, okay, I don't care for elliptically polarized wave. I'll be happy if I can find some solution for circularly polarized wave. Let's see, what do we do for that? So, for circularly polarized wave, I define a quantity B, which is a combination of By and Bz. By plus Ibz defines the right-hand polarization, and By minus Ibz defines the left-hand polarization. So, lo and behold, we can simplify our vector equation to somewhat similar equation, simpler equation shown here. It is still a nonlinear equation, all right? Supposing for a minute this term was not there, then you would immediately realize that the equation is nothing but the Schrodinger equation, which we studied in our very first course in quantum mechanics. But here we have this additional term. It doesn't matter. And I'm pleased to tell you that we have been able to solve this equation exactly analytically. And the solution I'm showing here, don't worry about the mathematical details of the solution. All I would like to say that these solitary wave solutions that we have obtained, these are stable solutions. And the stable solitary waves are called solitons. A word of caution for the young students here. In the literature, there's a big confusion. People use the word solitons without caring whether the solitary waves they correspond to are stable or not stable. Please be careful. What I would like to tell you here is that these solitons move with a constant speed. Again, don't worry about other factors that are involved. The result I have shown you in the previous slide, for that we had considered a homogeneous plasma. That is a plasma which had uniform density. And we found that in that case, the solitons are moving with a constant speed. But very often we come across inhomogeneous plasmas with non-uniform density. So we repeat our calculations and we find that in this case, the solitary waves or the solitons do not move with constant speed, they get accelerated. And this acceleration can give rise to anomalous heating. And I am pleased to tell you that this could be a potential source for the solar coronal heating. And these nonlinear Alvin waves have been observed in coronal region. So we have a reason to say that this could be a source for the coronal heat. Now, what is this puzzle about solar corona that I'm talking about? I'm showing you this. The core of the sun has a temperature of about 11 million degrees. So as we come out, we expect the temperature to go down, and it indeed does. In photosphere, the temperature is only 6,000 degrees. But when we come out to the another layer called corona, the temperature, instead of being less than 6,000 degrees, it is of the order of billion degrees. So this is a big puzzle. It has not been solved till today. You will be surprised. And in fact, there are probably number of sources which give rise to this heating, including the one that I have mentioned about accelerated Alvin solitary waves. Let's see what else can we do with the vector equation that we had derived. Supposing I say, okay, I'll be happy by just considering the localized stationary wave. But I would like to keep the ellipticity. In that case, I can make a simple transformation and take my words that complicated vector equation can be reduced to a set of these two much simpler equations, where H is the Hamiltonian of the system. I'm not giving you a complicated expression for the Hamiltonian because that shouldn't bother you. All I would like to say that the Hamiltonian is a quartic in B. That is, it's fourth order equation, which has a minimum, another maxima, and a double root called the saddle. This is the saddle point here. These orbits that I am showing in the phase space of By and Bz correspond to the constant energy orbits, the magnetic energy, of course. Now, if we start with the Poincare point on this orbit, all the Poincare points afterwards will fall on this very orbit. Absolutely no scattering. The magnetic field corresponding to these orbits, which are outside the saddle point, the magnetic field is larger compared to the ambient magnetic field, and we call these as bright solitons, which happen to have the left-hand polarization. These are the solitons for which the magnetic field is less than the ambient magnetic field, and we call these as dark solitons. They happen to have the right-hand polarization. We have a third type, the banana-like orbits. They have the mixed polarization. So these are the three different solutions that we obtain for our localized stationary waves, elliptically polarized waves. I remind you of the harmonic oscillator that we had considered earlier. There we had found that when the oscillator was driven by some external source, that showed us the phenomenon of chaos. So if I do the same thing to the system that I have already talked about, that is of Baldwin waves, and if I drive these waves, even by a very simple harmonic driver of frequency omega, can this driver has to be an external driver? And my answer is, supposing in natural plasmas, where we observe Baldwin waves, there is a big possibility that there may be another mode coexisting. In that case, the second mode can act as a driver as far as Baldwin waves are concerned. So in the presence of a driver, we go back to our MHD equation, rederive the equation, and we come up with a set of three equations which govern the localized stationary driven Baldwin waves. So this set shows that the system has 3 degrees of freedom, By, Bz, and theta, which is related to the frequency of the drive. If these two terms, A is the amplitude of the driver. If there was no driver, we go back to our system, which had 2 Hamilton's equations. We solve this set again. On the left-hand side, I repeat the figure that I had shown you earlier. When we put in the driver, we find that the scatter starts in the vicinity of the saddle point. You increase the strength of the driver, the scatter increases. And in this particular case, when the driver is, say, 0.3, the amplitude of the driver is 0.3, the system is almost chaotic. In this figure, You see all these are concrete points. I'm not showing you the orbits here because that will make a mess of it. I would like to show you the important role that the polarization of the driver plays in this context. Let's first take the left-hand polarized driver with omega equal to -2. As I said, to start with, the scatter starts near the saddle point. Scatter increases as you increase the amplitude of the driver. And look at this figure. It's almost chaotic, except for this region. And what is this region? To remind you, it is this region, which corresponds to dark solitons which have right-hand polarization. So what is this telling us? That the left-hand polarized mode does not interact at all with the right-hand polarized solid. This is what we call coherence in chaos or order in chaos. And we have a beautiful example of this in the Jupiter, whose atmosphere is chaotic, but besides that, we still have a coherent great red spot. Beautiful picture, which was taken by NASA. Now you might ask me the questions that the statement I have made about non-interacting left-hand polarized driver with the right-hand polarized soliton, how far it is true. To satisfy ourselves, we repeated the calculations with right-hand driver. And look at this figure. The region which was not even touched upon becomes completely pure. So the polarization is playing an extremely important role in deciding under what conditions the system can become pure. I'm not giving you all the mathematical details because if I start doing that, then probably I'll have to give you more than 12 lectures. So let's not worry about that. Now, I have made the system quite complicated, but I'm going to introduce another complexity. Supposing my system is dissipative. So far, we have considered non-dissipative. And I told you earlier that in dissipative systems, we can have attractors. Some of you might raise the question that why I'm introducing these complexities one after the other. Why couldn't I introduce all of them in one go? Yes, I could do that. And I could get the final results also. But then I won't be able to make anything out of the results that I would get. By introducing these complexities one by one, I can keep a full track of physics behind the problem. And that's the way I work, as a matter of fact. Now, in this, what I'm showing you is the evolution of the attractors that appear in this dissipative system. The evolution with an increase in the strength of the driver. In this figure, I'm not showing the strengths, but I'll give the numbers in the next figure. But keep in mind the labeling that I'm showing here, especially the figure label I. This is a complicated structure. It's a complicated attractor. Should I jump and say that this is a strange attractor? The answer is no. We should be patient. We will have to show that this attractor has a fractal dimension. Only then we will be able to say, yes, it is a strange attractor. In this figure, I don't know if you can see these two dots, they correspond to two attractors. Earlier, in case of the harmonic oscillator, I had shown you that the driven harmonic oscillator goes into chaotic state through successive period doubling bifurcation. Here, in case of driven dissipative plasmas, the Alvin waves become chaotic through distinct channels. The first one near the saddle point. Mind you, the labels A, B, C, etc. are the ones I showed you in the previous slide. These ones, okay? And what you find is that the two attractors that I had shown in figure label A, they go through large number of period doubling bifurcation and the waves become chaotic. Similar thing happens here. But I would like to draw your attention to this chaotic region. So on the top, the numbers I have given, they correspond to the amplitude of the joint. And see that the amplitude is increasing from left to right. This chaotic region, in spite of the fact that I'm increasing the amplitude of the driver, unlike this case, when the strength of the drivers are increased, the system became chaotic. In this case, when we increase the strength of the driver, the system is coming out of chaos. This is what we call the self-organization. The second channel through which chaos can take place, for that we go to the minimum of the potential that we have talked about. Here also we see a period doubling bifurcation, another period doubling bifurcation, but immediately there is a coalescence. Immediately after that, we start seeing chaos. And this chaotic region corresponds to label I. And to remind you, the figure in label I, this is the complex attractor that we have. We have calculated the dimension of this attractor and we find it is 1.57. So indeed, it's a fractal dimension. And now we can say that we have a strange attractor. So the sudden transition to chaos is taking place simply because of the presence of strange attractor. So now we come to another fascinating subject of fractals that I'll be discussing now onwards. But before I do that, I would like to show you two slides to tell you that there are ways of reducing the chaos in the system. Here we are showing you the results where we have introduced heavy ions like oxygen. And I'm talking about the cometary plasmas, which do show the presence of oxygen ions. But earlier we had talked about simple plasmas with two species only, like hydrogen plasma with electrons and protons. But here we are talking of plasmas which have heavier ions also. If it has only one type of heavy ions, it will be 3 species plasma, but we can also talk about multiple species plasma. We'll have to do the calculations all over again. you find that in case of two species plasmas, our system had become chaotic when the amplitude of the driver was 0.3. It had become almost chaotic. But now, in the presence of oxygen ions, we find that even when the driver is much stronger, say 0.8, we do see some chaotic regions, but we also see still many periodic orbits. The driver has to be extremely strong with amplitude, say 5.0, when it becomes completely chaotic. So certainly we can say that by introducing the heavy ions, we have been able to reduce the chaos in the system. Okay? The similar thing can be done in laboratory plasmas. We can introduce heavy ions as some sort of impurity in the system and try to reduce the chaos. Give you one more example of controlling the chaos. On the left-hand side, I have given you the results for the dusty tails in comets. And these dust particles can be really very, very heavy. On the right, I am showing you the results for the rings of Saturn. Hardly any chaos you see. So we have been able to succeed in reducing the chaos in the system. Okay, now let's go to the discussion of fractal. And I have already told you that the fractals are fracturized by fractal dimension. On top of it, a fractal has self-similar properties. It's a never ending pattern. When you change the size of the system, the patterns do not change. They are scaling wave. And in a minute, I'll show you that nature is full of fractals. It was Mandelbrot who was the first one who showed the self-similar properties of the very complex, irregular shapes of nature. Let's see where we can find these fractals. We can find them in smart science, maths, and arts. And I'll talk about science and maths only. Here, a tree in nature. You change the size, no change in the pattern. Absolutely no change. In maths, in geometry, take this triangle. I show you a better figure of this triangle. It's called Sierpinski triangle. Let's cut this by this amount, and it will go into these three smaller triangles. Repeat it, it will go into 9 pinkish triangles. So every time you repeat this process, the number of triangles increases by a factor of 3. For such self-similar figures, we can determine the dimension of the system by this simple relation. The n represents the number of repetition, which in this case is 3, and d represents the dimension of the self-similar figure. If d was 1, right-hand side would be 2. D was 2, right-hand side would be 4. But we wanted 3. So very clearly showing you that the dimension has to be somewhere between 1 and 2. So that means the fractal dimension. You can find the exact dimension by just taking a simple log of this equation. More examples. of these fractals. You see the figures, lightning, pattern is not changing. Same thing with cactus, with spiral galaxy, and even with our lungs. Another example is a beautiful example of peacock. Okay, I have shown you sufficient number of beautiful examples of fractals. Now a little bit about their applications. The fractals have many applications in many areas of science as well as technology. I've given you a big list, and even this list is not exhaustive. There are many more applications. However, I'll just say a few words about 2 or 3 of them, like fractal antennas, computer chips, and maybe neural networks. Here you see a fractal computer chip. You can see the fractal nature, and it's so beautiful even to look at it. This was designed at Oregon State University in US. How about antennas for our cell phones? Certain. See, earlier we used to have a huge big antennas, but now in our mobile phones, in our cell phones, obviously the antennas are very tiny antennas. And how can we do that? That is simply because of the self-similar properties of the fractal antenna. What you are doing is you are making use of fractal self-similar property to maximize the effective length of the material that can receive or even transmit the electromagnetic radiation. A big advantage. Fractal antennas are not only compact, they also are multi-band and wideband. Besides their applications in cellular telephone, they have applications in microwave communication. On top of all these fractal antennas can operate at many different frequencies simultaneously. Huge, big advantage for the engineers. One example, it would be nice to give you from life science. You see, the medical researchers, they make use of fractal analysis to analyze the CT scans of the patients to determine how good are their lungs. The fractal analysis they also use in determining the health of the blood vessels in case of cancerous tumor that I'm showing in this figure. I would also like to show you the applications that both chaos and fractals have in the study of artificial intelligence. I would love to do it, but probably Vandana would say my time is over. But I would make a remark that as far as I'm concerned, I would like the students to know about application in artificial intelligence.
You can take some more time, Bimla ji.
Questions through email. So if Vandana permits.
Sure. Please go ahead.
Okay. Thank you. So in order to say something about the applications of my field, which is that of chaos and fractals. But let me make it very clear that artificial intelligence is not my field. But I find it so fascinating, maybe because it involves my specialized field, that I have started reading the literature. And after showing you 2-3 slides here, I will convince our young scientists in the audience that when they start working on their research work in a year or two, they can take up problems in this field. It's wide open. Now, if we want to really get into the field of artificial intelligence, we ought to know something about neural networks. What are neural networks? They are simply interconnected neural circuits, which in turn are collection of interconnected neurons in the human brain. You have any idea how many neurons does a human brain have? 86 billion. People say that India has huge population. Yes, it is true. But the population that we have is only 1.3 billion. And look at this number that we are talking about. Similarly, the number of stars in our entire Milky Way galaxy is about 200 to 400, almost comparable to the neurons that we have in human brain. So, once we know how the system works in the human brain, that would be very helpful in creating what called artificial neural networks. This artificial neural network is nothing but only a computational model that is designed after the working of neurons in the human brain. In other words, an artificial neural network is an attempt to simulate the network of neurons that make up the human brain. What's the big advantage? In that case, we are teaching the computer, which will be able to learn things and make decisions in a human-like manner. But please don't jump and don't think that the computer can replace human being. No. How do we create these artificial neural networks? They can be created, I would say quite simply, by programming regular computers to behave as if they are interconnected brain cells. Another tool that is used in connection with artificial intelligence is known as deep learning technology. This technology describes some types of neural networks and their corresponding algorithms through which we process the input data by means of a large number of layers of nonlinear transformation to get our output data. So far, there are a few algorithms available, and one of them is fractal algorithm. And that is where fractals are playing their role. Both the artificial neural networks and the deep complex learning technique, they play an extremely important role in artificial intelligence for solving extremely complex problems. Through this only, we have been able to have the automobiles, which are driverless automobiles, and many other examples like the light signals on the crossings. So these are the applications of fractals in connection with artificial intelligence. But how about chaos? Chaos is service artificial intelligence. I see that there are two big questions in this case. First question is it really necessary for artificial neural system to be chaotic? If so, to what extent can chaos be used to exploit, to improve the performance of our artificial neural system? I would like to tell you that there are two schools. One school feels that chaos is a very essential, and there's a second school, they say no, it's not. So here is the open field for these young researchers to get into. Dr. Freeman, who's a neurobiologist in Berkeley, he strongly believes that chaos is essential from the brain activity. He goes on to say that chaos makes all the difference between a human brain and a robot that can function only in a controlled environment. He further says, this is something very amusing as a matter of fact. He says that the non-chaotic systems which settle down to equilibrium states or to low-level oscillations, they cannot correspond. They can never correspond to the living human brain. They can only be indicative of coma or death of a person. And because of the limited time, I would not like to further elaborate on this, but I hope I have convinced the audience that the field is open and that they can straightway jump into that when they decide to go for the research career. And before I finally stop, I would like to thank the organizers, especially Vandana, and also wish all the young budding physicists great success in their future endeavors. Thank you again.
Thank you, Bimla for really a very, very impressive talk on the complex subjects of chaos and fractals and neural networks and connecting it all. I am also appreciate your advice to all the youngsters, including and even to us. There is a thing saying that don't give up. This has been, you're always saying that, and that's really nice. Many people have given the reactions in the Zoom, which amounts to clapping. If it's okay with you, we can take few questions.
Sure.
Okay. So I ask people to type the questions in Zoom chat, and I will ask the questions. So there are already a few
Make my lecture too simple for the students?
Sorry?
I say, I hope I have not made the lecture too simple for the students, but
No, no, it was very nice.
I wanted to convince them that there is nothing complex.
Yes, yes. I think no, I don't think it was too simple, but they would have really appreciated doing that. I'm sure of that. There are quite a few questions, so I will just try to go over one of them. So one is how these chaos patterns are found experimentally.
Mean?
How the chaos patterns are found experimentally.
Experimentally.
Yeah.
Yeah, that's what I showed. The figures that I had shown, this is exactly what you should do. Supposing you drive one of the waves which I had considered, or any other wave, or even harmonic oscillator for that reason in the laboratory. You would start seeing, in case of harmonic oscillator, that when there was no driver, it was oscillating with a single well-defined period. But when you drive it with certain force, you find that it's not being driven with a single period, but it starts showing you double period. So that is an indication that something is happening. It's no more as regular as it used to be in the absence of the driver. Make the system much stronger. You tune it, that you can do in the laboratory, and try to see the patterns, try to see the existence of the waves if you are talking about the waves. And you would start seeing that there's a lot of scatter in the system. And once you start seeing the scatter, then only say, okay, there is a possibility of having a chaos. So exactly the patterns that I have shown you will be available in the laboratory. In fact, in space, what we call, it's a big laboratory for us to understand how do we go about. What is our solar system telling us? We must learn from it. And that's exactly we are trying to learn, especially in connection with our fusion plasma, to get hold of the fusion energy.
So before I go on to next question, I want to tell you, Bimlaji, that many students, in fact, most of them have said that it was a wonderful lecture and thank you so much for the interesting talk, wonderful talk. So there are a lot of, I think they really appreciated it. That is good. So now I go to the next question. What is fractal dimension?
What is fractal dimension?
Yeah.
Fractal dimensions, as I showed completely, is not 0, 1, 2, etc. that we are used to. Okay? A fraction. Literal definition, a fraction, is what is defined fractal dimension.
Okay, there's a question why these waves are called solitary waves.
Okay, I could have given you the examples here. You know, what happens is, usually you have, I wish I had the blackboard here for to show you. Usually when you have the wave, say sinusoidal wave, usually, okay? But if there is a possibility, what I call a solitary wave, all you see is a single hum, okay? Long back, I think it was almost in 1834 or something like that, a Britisher, he was riding on a horse along a canal. And what he observed was this single hum that kept on going as such. And the beautiful part of this is that, as I say, if it is stable, we call it solitons. And solitons, what happens is, supposing I have two solitons which come and collide with each other. And after this collision, they come out and you will find that nothing happened to them. They stay as they were. So it's just because of single hump that we see instead of the oscillations, then we call it a solitary wave.
Okay, thank you. The next question is, what is the difference between chaos and complexity?
Chaos and complex.
Yeah, complexity.
Complexity.
Yeah.
Okay. There is a set of systems which are chaotic, but a certain type of chaos. And that is what we designate as complex. And for a general person, for a non-scientist also, or non-physicist, I would say that even a system which is chaotic is a complex system. But in the literature, they try to distinguish it a little bit.
There's one more question is, what can be the reason behind presence of accelerated solitary waves only in the corona for the sun? In the sun, solitary waves are present only in the corona. Why?
The waves that there are which have been observed in the corona, yes, first of all, there are regions where we do observe large amplitude waves, and we also have observations of solitary waves. As I defined, we have solitons also. And besides that, this gives me an opportunity which they can look into one of my other papers, that solitons are usually defined as the hum of the wave. But in even observations that we have in some of the natural plasmas, besides the hum, we also see the depression. And this depression is what we call, when we are talking of the magnetic waves, the depression is what we call the magnetic holes. They have also been observed. They can look into one of my papers.
Okay, sure, thanks. How can we measure fractal dimension from a chaotic system like dimension of neural system?
It's not that easy to explain. I mean, very coolly, I said that the fractal dimension, the case I was discussing was 1.57. Little lengthy calculations. So may I suggest the person concerned to look into the reference that I had given in my paper? It would be easily understood. And besides that, what they would find is the point I have not made during my discussion, that the strange attractor that we found has the self-similar nature, and we have shown that in the paper.
Okay. Yeah, so I think I have one question. I do appreciate you said some things in the middle of during the lecture about the open research areas and also the advice as not to give up. But I think it would be really nice if you can say a few words about this to these young girls who are going to be starting the research career. Some advice from you for them.
So you'd like me to tell you how I got into this?
That would be very nice.
Okay. Frankly speaking, I myself, even till today, I do not know the real reason how I got into this, except for the fact that right from childhood, I had been. Are you asking me how I got into the field of chaos or physics?
Either will be good. If you say about physics, that would also be nice for them.
Right from my childhood, I used to be very much interested in mathematics. Okay, and you will be surprised to know that till my high school, I had no science whatsoever. No science. Only when I got into the college, Then I took science as a subject, one of the subjects. There, of course, physics and other subjects also. And probably because of my interest in mathematics, I got interested in physics rather than chemistry, etc. I never liked chemistry, frankly speaking. And though, as I said, I started with my science only at college level, but fortunately, I got admission in BSc Honors at Delhi University. And then it was easy. It went on smoothly. The only thing I could say, if you want to know how I got into plasma physics, you see, I was a student at Delhi University. I did my bachelor's and master's from Delhi University. And at that time, the subject which I may say fashionable subject at Delhi University was particle physics. And I had gone for my PhD, as you mentioned in your introduction, to University of Chicago. So when I went there, I thought I would be working in particle physics. I'd gone with this idea. But it so happened that in the first quarter and also in the second quarter, Professor Chandrasekhar was giving a course in quantum mechanics, which I had taken. I'd taken both his courses. He was an excellent teacher, excellent teacher. And I was so impressed with him that I said to myself, forget about particle physics. I'm not going to worry about particle physics. I'll go and talk to Chandra. We used to call Professor Chandrasekhar Chandra. All his students used to call Chandra. So I said, I'll go to Chandra after finishing my coursework, etc. And if he accepts me, then I'll start working with him. So I went to him, and the first thing that he said was, this was a sort of a challenge. Those days, he used to stay almost 90 miles away from the main university campus at a place called Jerky's Observatory. And he used to travel to the main campus on every Thursday, stay overnight at Chicago, give his lectures on Thursday and Friday, and go. So when I went to him to find out whether I could work with him, the first thing he said, you know, I don't stay on the main campus, so you won't be able to get much help from me. Would that be okay with you? So this was a challenge. So I said, yes, I'll manage. Somehow I'll manage. So he accepted it. So that's how I started, and I went into this field, plasma physics.
Thank you. Thank you very much. I think I speak on behalf of all the participants and on the Vigyan Vidushi organizers team that very, very special thanks to you for joining us through this online session and give this wonderful lecture and a lot of motivation to our young participants. We will share your email address with them as you suggested. So some of them may even send you the questions. And I hope they'll go back and read into all the new topics which you have told them, particularly the neural network, so that it can be. Thank you so much, Bimla ji. It really was a great pleasure.
And thanks once again to all of you. Thank you.
Thank you.
Bye.
I may request